Segmentation exists to divide networks in ways that reduce exposure and limit how far an attacker or failure can move once something goes wrong. In flat environments, every system can potentially reach every other system, which means a single compromise often turns into a widespread incident. Segmentation introduces intentional barriers so that access paths are explicit rather than accidental, and so that trust is not implied simply because traffic originates inside the network. From a security architecture perspective, segmentation is one of the highest leverage controls because it constrains reachability before higher-level controls even engage. When segmentation is designed deliberately, it turns the network into a set of controlled pathways instead of an open plane where anything can talk to anything else. Before we continue, a quick note. This audio course is a companion to the CISS books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. Traditional segmentation approaches rely on constructs such as virtual local area networks, subnets, and routing boundaries to separate traffic. These mechanisms operate primarily at the network layer and influence which packets can be delivered from one segment to another. By placing systems into different subnets and requiring traffic to traverse routing points, architects create natural enforcement locations for policy and inspection. This approach has been used for decades and remains effective when designed carefully. However, traditional segmentation often reflects physical or organizational structure rather than application behavior, which can lead to coarse boundaries. When segments are too large or too permissive, they provide less containment than intended and create a false sense of separation. Security zones build on segmentation by grouping assets according to sensitivity, function, and access requirements rather than physical location alone. A zone represents a trust level, defining what kinds of systems belong together and what kinds of communication are appropriate. For example, user devices, back-end services, and externally exposed systems typically belong in different zones with clearly defined interactions. Zones help translate business and risk considerations into technical boundaries that engineers can enforce consistently. When zones are well defined, policy decisions become clearer because traffic is evaluated based on where it is coming from and where it is going. Poorly defined zones, by contrast, blur trust assumptions and make it difficult to reason about acceptable access. Microsegmentation takes the concept further by enforcing policy at the level of individual workloads or applications rather than broad network segments. Instead of assuming that everything within a subnet can communicate freely, microsegmentation defines rules for each workload based on its identity, role, and dependencies. This approach is especially valuable in dynamic environments where systems are created and destroyed frequently, and where traditional network boundaries are too coarse. Microsegmentation reduces implicit trust within segments by requiring explicit authorization for east-west communication. The result is finer-grained control that limits lateral movement even when attackers compromise a system inside the environment. Microsegmentation shifts segmentation from a network-centric model to a workload-centric one. East-west traffic, meaning traffic that flows between systems inside data centers or cloud environments, is often where attackers spend most of their time after initial compromise. Traditional perimeter defenses focus on north-south traffic entering or leaving the environment, which leaves internal movement relatively unchecked. Once inside, attackers exploit flat internal networks to discover services, escalate privileges, and move toward high-value targets. Segmentation and microsegmentation address this gap by placing controls inside the environment rather than only at the edge. Controlling east-west traffic forces attackers to cross monitored boundaries repeatedly instead of moving freely. This internal focus is critical for modern threat models that assume perimeter breach is possible or even likely. Policy decisions are at the heart of effective segmentation because they define which flows are allowed, denied, or subject to inspection. A segmentation policy expresses intent, describing which systems need to communicate for legitimate reasons and which communications should never occur. Good policy design starts from a default deny position and then allows only documented, justified flows. This approach reduces accidental exposure and makes unexpected traffic easier to detect. Policy must also account for directionality, protocols, and context, not just source and destination addresses. When policy is explicit and reviewed regularly, segmentation becomes a living control rather than a static configuration artifact. Network access control is another mechanism that complements segmentation by controlling which devices are allowed onto the network in the first place. Network access control systems evaluate device identity, posture, and compliance before granting access to specific segments or resources. This prevents unmanaged, compromised, or unauthorized devices from gaining broad network connectivity simply by plugging in or connecting wirelessly. By integrating admission control with segmentation, organizations ensure that only trusted devices can enter sensitive zones. Network access control also supports dynamic policy, adjusting access as device posture changes over time. Without admission control, segmentation assumes that all connected devices are equally trustworthy, which is rarely true in practice. Firewall placement is a key architectural decision that determines how segmentation policies are enforced. Perimeter firewalls protect boundaries between internal networks and external networks, but they do little to control internal movement once attackers are inside. Internal firewalls enforce segmentation between zones, creating checkpoints that traffic must pass through even within the environment. Host-based firewalls add another layer by enforcing policy directly on systems independent of network topology. Each placement has strengths and trade-offs in terms of visibility, performance, and manageability. Effective segmentation strategies usually combine multiple enforcement points to avoid reliance on a single control layer. Segmentation also reduces broadcast domains, which has both security and operational benefits. Broadcast traffic can leak information, amplify attacks, and consume resources unnecessarily when networks are large and flat. By dividing networks into smaller segments, broadcasts are contained and become easier to monitor and manage. This containment simplifies troubleshooting because noise is reduced and anomalous behavior stands out more clearly. From a security perspective, limiting broadcast scope reduces opportunities for reconnaissance and certain classes of denial-of-service attacks. Segmentation, therefore, improves both performance and defensibility by constraining unnecessary communication patterns. Identity-aware segmentation represents an evolution in how access rules are defined, linking network policy to users, devices, and services rather than just addresses. Instead of allowing traffic based solely on where it comes from, identity-aware approaches consider who or what is initiating the connection and under what conditions. This allows policies to follow workloads as they move and scale, which is especially important in cloud and containerized environments. Identity-aware segmentation also supports more expressive rules, such as allowing access only for specific roles or service identities. By tying segmentation to identity, architects reduce reliance on static network constructs that struggle to keep up with dynamic infrastructure. Segmentation designs must also account for shared services such as domain name system resolution, identity services, logging platforms, and update repositories. These shared components often need to be reachable from many segments, which can undermine isolation if not designed carefully. Treating shared services as implicitly trusted shortcuts creates high-value targets and broad attack paths. A better approach is to place shared services in dedicated zones with tightly controlled access and strong monitoring. This preserves necessary connectivity while still enforcing boundaries. Ignoring shared service dependencies is a common reason segmentation designs fail under real operational conditions. Change impact is an unavoidable consideration because segmentation increases complexity and can affect troubleshooting and deployment workflows. Introducing new boundaries means that connectivity issues may arise that did not exist before, and teams must understand how to diagnose them efficiently. Dependency mapping becomes critical so that legitimate communication paths are known and documented before enforcement begins. Without this understanding, segmentation changes can disrupt services and lead to pressure to weaken controls prematurely. Planning for change impact ensures that segmentation improves security without undermining reliability. When teams are prepared for the operational effects, segmentation becomes sustainable rather than brittle. Verification is how segmentation moves from design intent to demonstrable control. Verification activities include reviewing rule sets, analyzing flow logs, and performing connectivity testing to confirm that allowed and denied paths behave as expected. Flow logs provide evidence of how traffic actually moves, revealing unexpected communication that may indicate misconfiguration or compromise. Regular review helps ensure that policies remain aligned with current architecture rather than drifting over time. Verification also supports audits and incident response by providing concrete evidence of enforcement. Without verification, segmentation exists largely on paper and cannot be relied upon during incidents. Segmentation limits blast radius by shaping allowed pathways rather than attempting to secure every component in isolation. Traditional segmentation establishes coarse boundaries, while microsegmentation refines control to the level of individual workloads and applications. Together, they reduce lateral movement, simplify monitoring, and make trust assumptions explicit. Effective segmentation depends on clear policy, thoughtful enforcement placement, and attention to shared services and operational impact. Identity-aware approaches extend segmentation into dynamic environments where static boundaries struggle. When designed, enforced, and verified deliberately, segmentation becomes a foundational control that supports resilience and containment across modern networks. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.